Good afternoon. I want to welcome you all for joining us for the inaugural Stetson Technological Advances in Medicine lecture. And I particularly want to thank Tom Sullivan, President of the University of Vermont, for attending this important event in the college and I think in the university. This lectureship series was established with the generous support of Dr. John Stetson, a member of the UVM class of 1956 and the College of Medicine class of 1960, and his wife, Roberta Stetson, who was a graduate of the UVM class of 1957. In fact, I'm very glad that John and Roberta have their 3 children and really many other family members here in attendance today to help celebrate this lecture. I just learned in the last few minutes that the first graduate of the University of Vermont College of Medicine of the Stetson family was 130 years ago. And we have many other graduates of the College of Medicine, graduates of the College of Medicine, current doctoral folks working at the university, and a prospective student in our medical school with us today. John was a Rutland resident and a Wilbur Fund Scholarship recipient at the college, and he went on to have a wonderful 39-year career as an orthopedic surgeon. Recently, the Stetsons had 2 experiences that highlighted the impact of technological advance in medicine and inspired them to create this lecture series. The first was Dr. Stetson's own double knee replacement last year. And then during his post-surgical rehabilitation, the Stetsons learned about an innovative and minimally invasive procedure called transaortic valve replacement. All of our students and faculty are quite aware of that, that had completely changed the life of an acquaintance of theirs. As Dr. Stetson has said, medicine has gone from the horse and buggy of my grandfather to a supersonic technological revolution that is globally limitless. At the College of Medicine, we experience this growth in medical knowledge and advance in technology every day. This is why we've designed our curriculum to be continuously revised and evolving, and train our students to be lifelong active learners. We thank the Stetson family for establishing this series that will allow us to examine important advances in medicine in a continuing way, and we could not have found a more appropriate inaugural speaker on this topic than the person you will hear from today, John Abele. John will speak on the law of accelerating returns, the challenges facing the medical field as a result of the exponentially accelerating technological developments. Next, I'm going to introduce Mercedes Rincon, who is one of our finest researchers and whose work is accelerating developments in her own field, and she will be introducing Dr. Abele. But first, we'd like to hear from Jack Stetson himself.
They probably can hear me anyway. Just because I brought a written statement, don't worry, it's only about 2.5 minutes. Anyway, my wife and I are pleased to sponsor the inaugural lectureship, Technological Advances in Medicine. I look back on my legacy to Dr. Homer Bogue, my great-great-uncle, who graduated from UVM Medical College in 1886. And practiced in Bristol, Vermont, and my grandfather, Chester Waller, a surgeon who graduated from Baltimore Medical College in 1898 and practiced in North Troy, Vermont, by horse and buggy. What would they think of medicine today? Dr. Waller was a surgeon in World War I and founded a hospital, Riverside Hospital, Warren, Ohio, 1924. My mother was an RN graduate from Mary Fletcher Hospital. I began my education at UVM in 1952, 64 years ago. And with the financial help of the Wilbur Fund Scholarship, I was able to complete my 8 years at UVM and receive my MD in 1960. Without the scholarship, I wouldn't be standing here today as an orthopedic surgeon. Bobby and I are grateful for our UVM education and hope the lecture will bring new ideas to lay people, students, interns, residents, and nurses, attending physicians, and allied medical personnel for years to come. We are grateful to Rick Morin, Dean of the Medical School, and Gordon Jensen, Dean of Research, for selecting John Abele as our inaugural speaker for this lectureship. As the founder of Boston Scientific, he will bring us a world of experience and thoughtful advice. I also want to say, for every physician, there is a team of people providing necessary support to reach successful treatment of our patients. We need to thank them for their individual help and their support. In closing, I want to thank a special person who has helped Bobby and I initiate this lectureship. Meredith Armitage is that person. She is Senior Director of Major Gifts for University of Vermont Medical College. I would like her to stand up and take a healthy applause for all her work and the team that does so much for the University of Vermont Medical College. And now I leave the podium to the research director.
Good morning or good afternoon, everyone. It's a pleasure and an honor to introduce John Abele today. John, I define John as a true passion and inspiring entrepreneur. He got the degree, AB degree from Amherst College, but I think he's a self-taught person. He learned a lot from himself over a number of years. He worked in advanced instruments, and then soon after started as a president from Meditech for a number of years. And this was one of the pioneering biotech in the field of interventional medicine. And then in 1979, that's when he started his career as an entrepreneur, because he was the founder of Boston Scientific together with Peter Nicholas. John is a true believer and supporter of the concepts of design thinking. He's probably going to talk about what it means is within entrepreneurship, you have to first identify the problem and the need, and then you work to develop a solution for the problem and need. And that's something that not many of us do. We sometimes have some funding, and then it's like, oh, what can I do with this? So his goal with Boston Scientific was to improve the health system, and improve through developing low-cost, low trauma, and accessible to many people by developing devices primarily, but many other medical solutions, I will say. John, everyone probably is familiar with Boston Scientific, and many of these devices are approved by FDA and is well known all over the world. John has the ability not only to have invention, but also to disseminate his passion, his inventions. He has given many presentations all over the world, over 200 presentations. That's something unusual for people in the industry. He's author and co-author and leader in over 40 publications. Again, that's something unusual just from someone in the industry. But he's also well recognized because he's received degrees, honorary degrees from many institutions, honorary doctor in human letters from Amherst College, honorary doctor in science from Wentworth Institute of Technology, Honorary Doctor of Science at Northwestern University, Gold Medal Award by the Society of Interventional Radiology, Gold Medal Award from the Cardiovascular and Interventional Radiological Society, etc., etc., etc. So, and in addition, he has been in industry, but he's really participated in the in academic by all the presentations, and he also has over 24 patents, and that's a clearly demonstration of his innovation, his capability, his capacity for as an entrepreneur. I have the opportunity to meet John a little bit more because he's a member of the SPAR program consultant panel. And he's also now part of the external advisory committee of the ITRAP program that we just started for 6 states and is funded by NIH. So every time that I talk to John, I feel inspired myself, and I hope you can enjoy today the same that I've been enjoying for a couple of times before. So please join me to welcome John Abele today. Thank you.
Thank you. Well, thank you. That's a pretty humbling introduction. It's only down from here. That's always the feeling you have when you get a nice one. First of all, I'm very honored to be the inaugural speaker to the Stetson Lecture Series. And I think I'm probably a good choice in one sense in that I'm not focused on one area. This isn't business. This isn't a particular field of medicine. It's a broad spectrum. And so what I've done is I'm going to talk about the law of accelerating returns, which is something I'll explain a little bit more as we go through this. But it's recognizing that medicine is in an exponential time. And that's good, bad. And I'm going to talk a little bit about where we came from, or at least where I came from, or the field that I came from, and a little bit more interesting where we're going. And so let's start from, where did we come from? And I'm looking at it from the less invasive medicine side. And this fellow, this is from Life magazine. It's an ad for 1964, whatever it was. And the fellow on the right is a gentleman named Charles Daughter. He was a radiologist who went and dabbled in everybody else's business. He did some cardiology work, he did GI work, urological work, and so forth. He was a classic inventor, and but at the same time, he was in the field of radiology at the University of Oregon. And here he is exploring an idea. The idea is, can we operate on a leg that has a stenosed vessel without operating, without surgery? And what he's doing here is he's actually pushing a catheter through, that's been tapered, through the narrowed part of the vessel. And unfortunately, he also had a tendency to say, I am going to eliminate surgery. It's going to be replaced by this, which did not endear him to surgeons, and as a result, they called him Crazy Charlie, and as you can see from that picture, Life magazine went along with that. This gentleman is on the other side of the fence, so to speak. He was an inventor, and he wasn't just a mechanical genius, he was a chemical genius, an optical genius, an electronic genius, a polymer genius, and he did this all in his basement. And he is the person who started a company called Meditech that I joined to run. We started in the basement of this building, 800 square feet. That was our garage. My desk was right next to the furnace, so it was very dry. Anyway, that's the way you sort of start. I always felt that the productivity of any sort of project is inversely proportional to the resources that have been given to it. I visited Czechoslovakia in 1963 when you had to go through all sorts of strange walls and barriers and machine guns, things, and so forth. And their Czechoslovakian Academy of Science, which developed all the soft contact lenses that are used all over the world, they had a very basic but extraordinarily innovative laboratory. And that's what impressed me. And say, how do you create the environment where people can be creative? And a lot of people, I think, sometimes make mistakes and sort of over-resource them. This was our first product. It's a steerable catheter. There's a little joystick, if you will, on the left-hand side of that pistol grip. And you move that around, and the tip would go in any direction. It worked like a marionette. There were wires in the wall, but it was a fascinating and attractive device. And we used that steerable catheter in lots of parts of the body, because the body is made of tubes. And for us, this was simply an opportunity to put a catheter in another tube. The marketing, this is 1970 at the American Heart Association. Marketing at that time, all the companies were very small. And you'd go and get an 8x10 booth. It's sort of like, you know, the local fairs. And you would have your products, and the doctors would come up, and you'd talk to them. And that would be one of the few times you get to see these people, because they're very, very busy. Along the line, we used that steerable catheter as a technique to remove retained biliary stones. Quick fact, in biliary surgery to remove stones, about 10 to 15% in 1970. By the way, there were 500,000 surgeries done a year in the US and another 500,000 done in the rest of the world. But 10 to 15% of the time, there were stones left behind. And that's not a good thing. Recovery from surgery of the biliary is very painful. And if the patient was told that they had to have another operation, that was not pleasing. So what happened is we developed a technique with this doctor here, Joachim Berhener, German, emigrated to the US and then to Canada. And here we are in Warsaw, Poland. We had just been to Moscow in 1975, which is part of the Soviet Union then. And this was 6 o'clock in the morning, because we just flown in the night before and had a 9 o'clock flight. And it turns out the chair of the Department of Neurology had a retained stone. He walked into the room and lay down on the table. I had a sample, demonstration sample of a steerable catheter. We swished it off in alcohol, went to the table, and in 20 minutes, we had pulled out this retained stone, which looks right here. You can see the catheter with the 2 lines over there, and the stone is where the arrows are pointing. And this was actually a movie and showed this whole process. The doctor, and he was a doctor as well as a patient, jumped off the table and gave us both a hug. And it's a great rewarding sort of thing to see happen. What we did, the sort of the philosophy of what our business was all about, was to develop a technology that leads to products, that leads to procedures that reduces risk, costs, trauma, and recovery time. And we felt it was very important to talk about that's the goal, not to make money. You have to make money in order to survive. You have to have a budget. You have to be disciplined. But you have to have a mission if you want to grow and be effective. And that was our mission. And the idea is we were going to disrupt ourselves as we learned more and the community we dealt with learned more. But unfortunately, this was not well received by a lot of surgeons because we were a threat. We were a threat to their power and prestige and, of course, their financial situation. And so that was a continuous challenge for us. We were vertically integrated in the sense that we made our own extrusion in this tiny little extruder, and we made extrusions that were very, very small, but they had many lumens in them. That's examples of some of them. At the time, these didn't exist. Now, I didn't know that when we went into it, but I actually invited a professor at one of the local schools of polymer science to see if he had ways to help us make these even better and smaller. He took one look and said, "How did you do that?" And so I realized that this was a consultant job. The information was going in the wrong direction. So we used those extrusions and wires and so forth. It was a very interesting collection of technologies, materials technology, forming with extrusion and molding and so forth, and then wire technologies and coating wires with Teflon, where the wires are 5/1000ths of an inch thick, and that was impossible, we were told. Well, it's not impossible if you try it. Anyway, here are some of the examples of the catheters we made. That one up the top, you can inflate each balloon separately, and then you have access to the space between the balloons. What's the significance of that? Body is made of tubes, and that means we can isolate a section of that body and literally treat it without treating the rest of the body. It's the opposite of systemic application of drugs or whatever it might be. But you're always in this world of everybody wants innovation, and then they set up all these barriers to oppose innovation. And I got very interested in whether our tools could be used in the coronary artery. And this in the early 70s. And I talked to surgeons, cardiac surgeons all over the world. Came across this gentleman in Japan where they had actually experimented in 1969 with making a flexible auger that you would put in the artery and it would remove the obstruction. Now, obviously, there's a bit of a risk here. And that is why that product never really went anywhere, because it would go through the wall of the artery just as easily as it would go through the lesion. And at the same time, tried out making things ourselves. This is in essence, it's a guide wire, it's called. That's actually a spiral wire that's very, very flexible, and it can follow the vessels. And at the end is something that's very much like a Chinese finger puzzle. You can expand it by pushing it and then making it very, very tiny. So the idea is, how do you get into an artery and then enlarge something to remove whatever it's going to be? We never used that, but we tried it out in animals and so forth. That's the way you do it. And then along the way, I met a gentleman who had come up with the idea of a balloon that would expand the artery rather than a tapered catheter. Now, the advantage of a balloon that expands as opposed to a tapered is that you'll push it radially rather than axially. And people used to talk about the procedure being very much like a snowplow. Well, a snowplow is not what you want in the body, because you're just going to push the debris downstream. So this is the technique that was used, and a lot of people didn't think this was going to work either. But in fact, it did. And another thing is sort of to understand is, how do ideas get expanded? And it turns out Johnny Carson, who was the great night show host for many years, one of the best comedians out there, and he used to open his night show by going on stage and then swinging an imaginary golf club. He was a fanatic on golf. And he was told he had intermittent claudication that was giving him pain. He could only walk 100 feet or so before the pain would be really bad. And so he went to Cedars-Sinai, the Hospital of the Stars out in LA, and they prepared to do surgery, but they said, look, there's this new thing that's happened, and we're going to try it out on you. They put this balloon in there, and they will push the lesion to the side. He had told his audience of 20 million that he was going to be out for 6 to 9 months. But they're going to try this thing out on me, he said. It's a balloon, and they're going to push it, and I might be able to come back earlier if that works. Well, he was back 2 nights later. And he talks to Ed McMahon, who is his sidekick, because that's the way they do the thing, and basically explained to that audience of 20 million what this thing had done for him. And what was fascinating is the phone on every vascular surgeon's desk started ringing off the hook. And that became, if you will, the patient-driven reason it became widely accepted. It took a long time. Early on, there were a lot of complications, but at that time, there was a lot of patients. This was really about the time the FDA was starting to regulate, but they hadn't figured out how to regulate. But in fact, we talked with the FDA, and they told us, that's okay, just keep us informed. We're not ready to regulate these yet. And then, of course, they did. And then this guy here, his name is Andreas Grunzig, and this is the American Heart Association, 1976, Miami. He's holding our steerable catheter, because that was a way to get the balloon catheter into the position in the coronary arteries, which are sort of right here. And this poster is a classic example of both good science and great communication. He was based in Zurich, Switzerland, and he did work on cadavers. He did work on animals. He did work then on legs, and then he went to the coronary. But he showed the results in each case, and when he presented his data, he was very careful to present it in a slimmed down way, if you will, knowing that people would ask him key questions. But he was always prepared to answer those questions because he had studied every single one that they came up with. So he would go around and give talks at grand rounds and would just awe the audiences. He was very humble and mild. Have you ever met an inventor and a doctor? Who is those characteristics? They don't go together. And he understates. And it was, I would argue, sort of the reason that technique became accepted was that individual. And also this individual. Aki Senning was a cardiac surgeon in Sweden. He was world famous. He had developed the very first pacemaker. And he moved to Zurich so he didn't have to pay Swedish taxes. And, but he was sort of a god in Zurich. And understand Swisser Deutsch, Swiss-German sort of mentality. It's a very hierarchical, structured, here, professor, doctor system. Apologies for my German friends here. But that's the way it is. And it turns out that Senning became the patron for Grunzig. And his endorsement enabled him to do cases that he would never have been able to do in another environment. So you think about developments in history. Very frequently, there's somebody behind the scenes like that who makes things happen. It happens with you. You have mentors, you have patrons, but that's really important in the whole process of innovation. there's a story of what Boston Scientific did, but more importantly, what happened with the entire field of less invasive medicine, because it was in cardiovascular, and it was in urology, and it was in GI. In urology, there's a field called endourology, which the old urologists call end of urology. and so there was always this tension. I had written an article on collaboration for the Harvard Business Review. That's the cover of the magazine on the left where you see it says collaborate. And I had the temerity to ask if I could talk with the other authors to see if we could jointly write a summary of the different ways we looked at collaboration. And what was their response? We don't do things that way. Yeah. Academic collaboration, military intelligence, et cetera. Hey, a lot of collaboration goes on. I'm not saying that. But I'm saying the system is not designed. In academia, you were rewarded for individual success, not group success. Because how do you know who did it if it's a group? There's a very famous cardiac surgeon from the 50s and 60s named C. Walton Lillehei. And he talked about the 7 stages in the evolution of an idea. You talk about it, and they say it won't work. You do work in animals, and they say it won't work in man. After one successful case, well, you're only lucky. 4 or 5 cases, well, kind of highly experimented. Those are selected cases, so forth. 10 to 15 patients, well, it'll succeed occasionally in carefully selected, but most people don't need it. Sorry, I got to press the wrong button. And then you have a large series of successes, and they talk about, well, somebody in Shangri-La can't do it, or is having bad results, or whatever it might be. And then the final stage is, oh yeah, I predicted that. I would have done it a long time ago. This is the way most invention works, and just tons of examples of that. And oh boy, I'm pressing the wrong button again. Okay. Oh, how did I do that? I didn't think it was possible to do that one. There's innovation for you. And this is something in the entire design world. An awful lot of people are perfectionists, and they will, in essence, over-design the product. It was very fascinating as we developed these techniques. Probably the most important maker of endoscopes was Olympus in Japan. Even though when it was started in Germany, came to the US, American Cystoscope, and others, but Olympus really took it to a whole new level. They're very good at making complex things. But the problem was they would make simple things complex as well. And as a result, we made the same product, but with half the steps. And as a result, we were able to advance it. Okay, so that's the past. Where are we going now? How many of you read this book? This was 1970, Alvin Toffler. He died at the end of June. And Future Chalk was profound in the sense that he identified sort of a problem of innovation. And that is the rate, or the acceleration, if you will, of innovation is so fast that we can't manage it, we can't keep up with it. What does that mean? And it has government implications, it has scientific implications, lots of things. And it changes the way we govern, it changes the way we teach, it changes the way we assess. Think of the fact that we use clinical trials in medicine today to evaluate the safety and effectiveness of whatever therapy or diagnostic is being used. But the problem is we're able to develop these new ones faster, but our ability to assess them is not going faster. So there's a gap. And now by the time you find out whether it's good and bad, all you know is that it's obsolete. So it's a real dilemma. Ray Kurzweil is the inventor of the first reading machine for the blind. He's an extraordinary scientist, neuroscientist as well, and he is actually out now running Google's brain project. They are building a brain. Now, what could possibly go wrong? It's fascinating to see what he's done. He's a very prolific writer. He is the author of this singularity concept, which says we are getting close now to the time when computers will be more intelligent than humans. In some ways, there are a lot of us who feel that. We passed that a long time ago. But anyway, the observation is that the advances in technology are accelerating. This is a plot of mass use of inventions from literally late 1800s to today. And what looks like a straight line is not. That's a logarithmic plot. And what's really interesting is towards the end, the acceleration is accelerating. So this is the humbling factor that we have to accept. And we need to understand this because it's going to affect all of us. Think about it. It's fairly simple. You know, why is this happening? This is why it's happening. Everybody has more access to information. And you can also get in touch with people that you never could get in touch with before. You can create collaborations that would only have been, dreamed of years ago. The rate of new material development is extraordinary. If you go into the chemistry world, so forth. And these are enabling us to do things. Graphene, for example, is probably going to end up changing a lot of stuff. It's an incredible material. Right now it's too expensive, but it's a conductor, it's a superconductor, it's the strongest material out there. It's got amazing properties. It's a lot easier to learn new skills. You can find anything on the web. Now, you don't know how good or bad it is, but hopefully that's what you learned in school, is to make those judgments. If somebody makes a statement, did they back it up? And then, of course, there are more people who have access to these, so, of course, all those add up to rapid acceleration. And then you have the result of all of that, the hyperconnectedness, the democratization of knowledge. Well, that's great that everybody has this, but we're already seeing some of the negative aspects of the democratization of knowledge. And the globalization factor, that's very, very controversial, but it is sort of cat out of the bag. Shared economy is going to change the way business does and everything. Crowdsourcing is not a phenomenon. It's an entire field. There's lots of different ways that people collaborate. And it is a science in itself. Network science, in fact, is probably one of the most important, profound sciences that we're still trying to understand, because that's the way that little organ works. And of course, getting back to collective intelligence. And then, too many words on these slides, but the bottom line is, this is just a short list of the big trend of a lot of these things are converging. So you certainly see that today. I've talked about with several of you already the concept that in medicine, as you get smaller and smaller, you get into molecular phenomena, and it applies to any field. And then the convergence we're seeing. Oh, you can't get it out. There we go. And then one of the things, a very common term now in the business world, is VUCA. Volatility, uncertainty, complexity, and ambiguity. We're obviously going to get a lot more of that. And that has enormous implications on both how you learn and what you learn. So the important thing to get out of any educational experience is how to learn how to learn. And how do you do that with flexibility that you can't get otherwise? And you have a lot of people. Eric Topol is a cardiologist out in San Diego. The idea of, can we incrementally advance it, or do we have to destroy it along the way? Always an important thing to understand. Then we have the sharing economy, and what does that really mean? How is medicine going to be Uberized? Because it is going to be Uberized. And already you find lots of little models here and there. How is education going to be Uberized? Again, it already is. Khan Academy is sort of a variation of that. It's absolutely extraordinary. It's a not-for-profit, but it makes really good lessons available for lots of things and in bite-sized chunks. Robin Chase is the founder of Zipcar, another sharing model. The whole idea, the recognition that we all have this stuff that's around and it's not being used. Why not get a return on it? And maybe the car companies won't like that. Who knows? The idea of medical tourism, and literally, this is Devi Shetty in India, who developed a 1,000-bed cardiac care hospital, but he really turned it into a factory. And he now has built a hospital on the Cayman Islands, and he was actually going to come to the United States by building his hospital on Indian reservations. Now, you have to give him credit. This is a novel idea, because that's sort of outside the United States. So he thought he could get outside of rules and regulations. Not the case. There are lots of organizations now. This company, Transparency Life Sciences, is an open source development group. Sage Bionetworks is a consortium of a whole series of companies who are saying, yes, we're competitors, but we need to do some pre-competitive collaborative research. They actually looked at a model called Semitech. I don't know if any of you have ever heard of that, which was in the early 80s when all the semiconductor companies got together because they felt they were losing out to other world competitors. And they got all these people who are arch competitors to share basic research knowledge. Everybody wins. It's understanding how to avoid the tragedy of the commons. You need the commons. Patients Like Me is also a phenomenally, almost obvious, but a not paid attention to sort of field. It brings together patients with unusual diseases. And it brings together physicians who are working on those diseases. And it did not have a lot of excitement in the medical community initially, but in fact, I think they do appreciate it now. And the power of the data that they are getting, and the fact that in many cases, I guess they're getting amateurs to actually do some pretty impressive scientific research that has value. But at the very least, the patient gets to speak to people like them. And the value of that is great. Foldit is a rather famous example of how you can harness. This is crowdsourcing at a pretty high level. And it was trying to figure out how certain proteins fold. And in this particular example, the one they'd been working on for 15 years, couldn't figure it out. They turned it into a game, and it was solved in 3 months. The iWire is working on the same area. It's a massively multiplayer online game, MMOG. And again, it's got 80,000 players now. And they are rapidly advancing the connectome of the brain for the eyes. There's lots of interesting delivery models being experimented with. as well, and focused on choice, transparency, and participation. All of those are just fundamental. Having a proper attitude is great. And then recognizing that exponential medicine, there's a meeting going to take place in October, which will have, incredible collection that is not focused on a particular category of medicine. It's all over. Very much what I hope this series will turn into. And here's something that was developed a while ago. This is not a company. This is an example of using a fairly old principle, Eulerian amplification. Euler was a mathematician in the 16th century, middle 1700s, and his work focused on the magnification of small differences. And what's happened here is a video is taken of this gentleman going from left to right, and then it's magnified 100 times in the bottom. And guess what? You can see the color change in his face, which is amplified, which comes with every heartbeat. And let's see, I have to do this over here. Watch the face on the right. You should see that with a baby. It's amazing. Now, what's interesting, and hopefully some of you have some imagination or something like this, there's a lot more information there than just the pulse rate. I think you're going to be able to get cardiac output out of that. And, but it's going to require big data and mathematical analysis to do it. Another one that is particularly fascinating now are electroceuticals, the whole idea of trying to produce pharmaceutical effects or physiologic effects without pharmaceuticals, but using electrical stimulation. This is an example of one where they've got a particular stimulation format that tends to suppress inflammation in tissue. So it's doing drug work with electricity without side effects. This one is interesting. So that's the, it's on a thumb. The microsensors. These are microsensors that don't need batteries, but you can quiz them with ultrasound. The ultrasound both stimulates and sends a signal back so that you're going to be able to have, if you want it, sensors around your body that can either remotely tell your doctor what's going on, but more importantly, might tell you what's going on. The idea of getting faster feedback on your physiologic self, the so-called quantified self, is growing. It's not just the Fitbit of the world. It has real medical applications. And here's an example of a few people who are fairly significant, who are putting a bet down, $700 million over 7 years. So GlaxoSmithKline and Verily, which is Google's life sciences division. So they've formed a partnership. They really believe this is going to be a huge deal. But they also know that it's going to be a lot of research that has to take place as well. This is an example of how ultrasound can be used in the brain. So in this case, it's not inquiring of a sensor. It is actually influencing the behavior of certain cells with the goal, in this case, of trying to treat, not amnesia, the thing you can't really forget. Okay, and I love irony is a wonderful gift. And the whole question of CRISPR, don't know how many of you are familiar with that, but it's basically the ability to edit your DNA and genes. And it has now gotten to the point where it works like a word processor. So that doesn't guarantee you'll do it right, but we've been able to clip DNA for a while, get DNA chips. But the idea of putting them together in the right order to cure various diseases has been a dream. Biofabrication. There's a lot of this building body parts, if you will, that is going on in a way that can take your own cells and put it in a frame and then grow an organ. This group, whose meeting is in October in North Carolina, has actually a whole floor where they are making body parts. Now, obviously the thing that sort of comes to mind is, what's ethically correct here and when are things ready or not ready. But when you build these parts, if you build them out of your own cells, you solve the immune problem. So it's a big deal. And the obvious question is this one: how are we going to prevent misuse? And it's great to get people together and say, we'll make rules. But unfortunately, you can buy a CRISPR kit for $250, and that doesn't, give you the lab, but the lab is not capital intensive. So I would be willing to bet any of you right now we are going to be seeing people who are doing experiments that we wish they didn't. The Chinese have already done some work on babies, but I think that was not that was an acceptable one. But it causes you to think about reinventing discovery. And what do you do to get the right people involved, not just to discover the answer, but to discover what you're going to do with the answer when you get it. Let's plan ahead. And some people have been doing that, but obviously that did not happen with CRISPR. I've been very intrigued with the fact that UVM has a partnership with IBM on the Watson project. I'm not sure how broadly it's applied, but the implication for how these things are going to go into the augmenting human intelligence is going to be a big deal. Juan Enriquez, the lead author on this book, a fairly new one, is a biotech guy, but he's also a physicist. And this book is trying to project how we are going to change. And basically what he is saying is that within this century, we are going to see changes that will be non-Homo sapiens. We are going to evolve ourselves as a race. But what he's really saying is it's not that we're going to have computers there and humans there. We're going to have a hybrid. Now, one of the things that I've been involved with, this is a project at the University of Toronto that does use Google Glass. It doesn't have to be Google Glass, just the idea of having something you can wear where you can see a screen without being too obvious about it. And it's focused on business, not medicine. The idea of if you are going to be a leader in dealing with very, very complex phenomena, how do you deal with managing your emotions and managing your brain, if you will, so you think the best? More importantly, if you're in a group, how do you manage the group to optimize the likelihood of their thinking at a high level? Whether it's working memory, deductive reasoning, all these sorts of things. And what the tools are for this experiment, if you will, are a whole series of sensors that can be worn on the wrist, like a Fitbit, except they measure a lot more. They measure stress in particular. And stress affects all of our lives in ways that are very subtle to us personally. And we sometimes make really stupid decisions. And if we could track that stupid decision making, perhaps we could make fewer of them. But it goes down to EEG analysis and the ability now using Wolfram Alpha on EEG to actually predict what's going on is phenomenal. We can't get a 3D real-time voltage map of the brain, but that's going to happen. And I submit when that does happen, we're going to be able to do more of these things, and hopefully we'll use it for good purposes, not bad. Just last month, a group of people published in Nature this discovery of basically doubling the number of regions of the brain that they can assign specific functions to. That's a little bit of a fuzzy thing, but it's a significant advance. And just to tell you that I'm not just a business guy, I'm also a customer. So one of my jobs has been to test the diseases that we treat. This is my stroke, and I've mostly made it back. This is not me, and this is my last slide, but this is a don't jump to conclusion slide. This is an extraordinary story, and this person has lost 90% of his brain, but he is still functioning. He is a parent, he has children. He's not in the high on the IQ list, but the integration capacity of how the rest of his cells adapted and connected to do functions that they didn't do before. I think that's something that is, you always have to remain humble on any of these things. You never have the whole story. Thank you very much.
Maybe we have time for one question or two questions, if anyone has. Oh, there's one question.
I'm really fascinated by what you just presented, and I'm wondering, is there a common vision of where science, technology, especially medical technology, is going? Because I can foresee easily, let's say within the next 100 years, that medical technology, scientific technology will have evolved to the point where humans, barring the unpredictable homicide, humans will be able to live as long as they like.
I have a number of friends, actually, who are in the life extension world. And, whatever you might think, why not? There's a lot of people doing it. And actually, Ray Kurzweil, you saw earlier, is one of them. The problem with any of these things is it's just like medicine. If we really succeed so that fewer people are dying than being born, do you understand what might happen? And as a society, we have not figured out how to adapt to big changes in population. And Europe right now is getting that worse than us. But as climate change, grows, you can certainly envisage people moving around in this continent as well. And according to Kurzweil, the singularity, which is when the computers sort of become more powerful, is going to occur in the 2030s. So it's this, couple of maybe 20 years. That capability will be there. And these are challenges that we don't have good mechanisms for addressing, and the we being, global citizens, because we're not very good in getting countries together, witness the UN, and particularly for things like this. So it's going to be challenging, and I think we're probably going to have a few disasters that may remind us that we have to solve the problem first.
One more?
In your travels, do you see the same enthusiasm and entrepreneurship that you see in medical device, technology, biotech, being brought to the ethical questions that are being raised with this rapid scientific expansion? As was sort of alluded to, the question of ethics and medical ethics, is the field of medical ethics accelerating in any rate going to keep us up with this, or do you just foresee a big problem and something?
I think the latter. I think the whole idea is ethics a science? Look at where ethics as a subject is taught. And it's siloized the way you do things in academia. And to look at it and very, very broadly, it is tough. So I think we're probably going to have a reminder event that may cause us to rethink. It's very difficult looking at the world through U.S. eyes. U.S. is very entrepreneurial and accepts it. The rest of the world does not accept it in the same way. But it is interesting that entrepreneurialism is growing. There's an organization that came out of Boston called Mass Challenge, which focuses on startups and things. Did I send you some of that? Okay, I'll do it. It's now the largest startup accelerator in the world, and they have programs in half a dozen countries. And anybody in the government business says, I think we need, whether the word is entrepreneurship, but we certainly need creative solutions, and we don't want to lock ourselves out with rules or regulations or laws that prevent us from coming up with a better model. And there are certainly those things here. There's the Creative Commons. I don't know if you're familiar with that organization on the West Coast that is looking to try to address this whole issue of proprietariness. It's focused primarily on copyright, but I think, at least I know I have a plan for patents, but I don't think nobody will buy into it. And by the way, there are a lot of solutions in medicine that don't get pursued because it's not obvious how you can make money on it. And that's unfortunate. We have to figure out avenues to, monetize is the wrong word, to create value that benefits everybody who does it well. That's a different economic thinking. And I think we're going to see a lot of models coming out. So, thank you.
Well, thank you again, John.
Thank you.